Okay, hey there, welcome back. So in this video in our series on introductory econometrics, we're going to be continuing our sub-series of lectures on expansions of our basic econometric analysis. And in this video, we're going to be talking particularly about dummy-dependent variable techniques. These include the linear probability model, the binomial logit model, and then we'll just touch briefly upon a couple additional more advanced dummy-dependent variable techniques. In each of these models that we're going to be covering in this lecture, the key thing about what we're doing here is that the dependent variable, the left-hand side over here, is a dummy variable that is taking on a binary value of either 0 or 1. So you can think of this as an event that occurs or doesn't occur. The person buys the item or doesn't buy the item. The light is on or the light is off. A person chooses to do this or they choose to do that. In each case, the choice is binary. And what we're trying to do is to predict the probability that that outcome is, let's say, 1 or 0, right, given the values of our independent variables or our explanatory variables and the estimated coefficients on them. Okay, so you can think of this, in a practical way. You might think of this, what are the odds of a person buying an item given a series of explanatory variables? Okay, so the most basic of these is this linear probability model that we see over here. So this is where we have essentially our now easily recognizable linear form estimated relationship with, in this case, an intercept of beta 0, two explanatory variables x1 and x2, and their associated estimated coefficients of beta 1 and beta 2, and then what we hope to be a normally distributed error term. Now, of course, this is very straightforward, right, this model. But there are a number of problems associated with these types of models. First off, the adjusted R-squared, does not accurately measure fit. Okay. Second, the estimates of D are not bounded by 0 or 1, so we can certainly end up with a predicted value of D that is less than 0 or greater than 1. And then third, the error term is not homoscedastic as we need it to be, nor is it normally distributed. So we have a number of problems associated with the error term in these cases. Now, for some of these problems, there are remedies that we employ. The first of these is to create what's often referred to as a pseudo R-squared, which we're going to note like this from now on in our lecture. The number of ones that we correctly predict, the number of zeros that we correctly predict, the average of those two values is going to be our pseudo R-squared. Okay. We can, in these cases, we can assign values of 1 for all estimated values of D that are greater than 1, and 0 for all negative values. And so this is a way of correcting for the fact that our estimated dependent variable, D, is not going to be bounded by 0 and 1. We can simply force boundaries onto it. Okay, we interpret these estimated betas, in these models, as the percentage change in the likelihood of D being 1. So for example, a estimated beta of 0.5 would be telling you that a 1 unit change in the value of that explanatory variable would produce a 50% change in the likelihood of your dummy dependent variable being 1 rather than 0. Similarly, an estimated beta of, say, 0.21 would suggest that a 1 unit change in the explanatory variable x related x to that is going to produce a 21% increased likelihood of D being 1 rather than 0. Okay, so the interpretation of this model is fairly straightforward. However, it is not a very satisfactory model in most cases because of the sort of conclusions that you're forcing upon it. A solution to that, or at least an improvement upon that situation, is to use what's called a binomial logit model. And what a logit model does is it avoids this unboundedness problem by utilizing a cumulative logistic function, which we see. I'm going to use the cursor this time because it's pretty small. Okay, so we'll notice our standard, or what looks to be our standard linear form here: beta 0, beta 1, x1, 1. You can't do subscripts of superscripts. Beta 2, x2, so on and so forth. We notice our regular form here. That this relationship then is going to produce the probability p that our dummy variable takes on a 1 value rather than a 0 value. Okay. Now we use this alternative form because we cannot use OLS because it's not linear. Okay, and so instead we use what's called a maximum likelihood process. And now a maximum likelihood process works a little bit differently than OLS or a lot of other estimation methods that you might employ because it is an iterative process. What the maximum likelihood is doing, what the maximum likelihood process is doing, is it's choosing betas that maximize the likelihood that the sample value of the dependent variable are observed. Okay, so it's finding the function that fits the data associated with the binary outcome. Okay, now I'll show you a graphical representation of this here on the next slide, but maximum likelihood estimators are unbiased so long as the error term is normally distributed, okay, which is really something we need to keep an eye on in these types of estimation techniques because it, as we saw on the previous slide, there is a strong possibility that the error term will not be normally distributed. So running residual diagnostics is an important part. Excuse me, I'm having a hard time speaking today. Being careful running your residual diagnostics is an important part of utilizing these types of models. Okay, so over here now we see sort of the difference between the linear regression on the left that we're regular, so we're comfortable with, or we've talked a lot about through several of these videos, and then what we're discussing here, logistic regression. So you'll notice that the logistic regression is bounded by 0 and 1, right? The form of the estimated relationship is asymptotic to the value of 1, and the same for the value of 0. So it approaches, but only at the limit does it approach 1 or 0. Okay, and it takes on this sort of S-style shape rather than the linear shape that we see on the left over there. Okay. And so what your maximum likelihood process doing is forcing the logistic function that best fits the results that you've observed. Okay, so remember the results are all 0s and 1s. So this is the result that best fits the likelihood that your quantity of observed 1s relative to your quantity of observed 0s is consistent with this relationship. Okay, so now when employing logistic regression, it is quite a bit more complicated than simple OLS style regression in terms of interpreting the coefficients or the betas. Okay, there are several different processes for interpreting the betas. One way to do that here, okay, enter the mean values of all the independent variables, right? So if we have x1, x2, x3, if we take all the observations of, say, x1, we take the mean value of those observations, all the observations of x2, take the mean value of all those observations, and so on for all of our independent variables. And then we calculate for the estimated value of d we arrive, of course, at an average value of D. Okay, now it's tricky, right? Because it's an average value of zeros and ones, right? So it's a little unusual. Okay, and then we can take that that D, right? Change whichever independent variable we're interested in knowing the specific relationship with. Change that independent variable's value by 1. Then rerun the regression. Take the new estimated value of D. Remove the average value of D that we calculated a moment ago. And that difference between those two D's is our marginal impact, or our 1 unit change impact of a change in that independent variable on our dependent variable. Okay, so to take a sort of example of this, or to sort of walk through this, let's say the likelihood that a person buys a thing. So either they buy it 1 or they don't buy it 0. Okay, and let's say that that's a function of a series of independent variables. And maybe it would, one of them would be whether the time of day it is, or something like that, or whether it was advertised, or how much was spent on advertising, or something like that. So we want to know, like, well, should we, if we increase advertising by, say, another $10, how much does that impact the likelihood of a person buying a thing? Well, we would want to take all of our average independent variables, including our average value of our ad expenditures, use all those averages to calculate a value of D, using, just solve it out, right? Estimate the value of D from there, then change our ad expenditures by 1 unit, re-estimate, okay, and take a new value of D, and the difference between that D that we get and the original D is going to be the marginal impact on the likelihood of a purchase given a 1 unit change in expenditure in advertising. Okay, all right. So that's kind of long. Another way to get a sort of rough estimate of what you're going to do is to multiply the Logit estimated betas by 0.25. Okay, and in doing that, you can then get a rough estimate of what the linear probability estimate is going to be. So let's say we've got a Logit beta of 2. Okay, well, dividing or multiplying that by 0.25 would give us a half, right, or 0.5. And then we can interpret that 0.5 in the same manner we did with the linear probability estimates a few moments ago. That is to say that a 1 unit change would give us a 50% increased likelihood of D being 1. Okay. All right. Now I put down here at the bottom again, we still need to be concerned about the normality of the error term distribution. So again, running diagnostics on the residuals, important part of these processes. All right. In the remainder of this time, I just want to talk briefly about a couple other techniques that we would use to do this sort of analysis. One is a binomial probit model. Okay, so probit models are very similar to logit models, but the cumulative distribution function is not the same. So the logit model is using the logistics form, whereas the probit model is using an inverse normal cumulative distribution function. Okay, so the mathematics is a little more complicated of the probit model, and the interpretation of the betas is quite a bit more complicated when compared to the logit model. Generally use these as, so they're used in literature where it's just common to use probit models in some subfields. Probit models are what are used, right? And so if the field is operating using probit models, then that's probably what you want to use. But to say any more about that is really beyond the scope of this lecture and this series of lectures, which is on, of course, introductory econometrics, and probit models are probably not introductory. Okay. Then finally, we also have so-called multinomial models, right? And these are used when we have more than 2 qualitative choices. Now, this actually comes up. It's not uncommon, right? So let's say we have a binary choice, or a series. We have a series of possible outcomes, but that series of possible outcomes is the product of a series of discrete binary choices. So I choose A or B, and then once I'm at B, I can choose C or D. Okay. Now there are a series of possible outcomes, A, C, and D, right? 3 that are the result of a 2-stage binary process, right? A or B, and then if B, then C or D. Okay. These processes can be used utilizing these multinomial models, which again, to just more than introduce them would be to go beyond the scope of what this course is. Okay. That's really it for this time. This is a sort of quick one, right? Because it's not getting into it too much. Please do keep in mind that this is sort of just the introduction to the theory in this case. Normally it's more in-depth discussion of the theory of these things, but we're getting into the extensions at this point. Please, if you're interested in sort of how we apply these models in actual work to actual data, please see the accompanying videos where I utilize the eViews software and we apply what we've learned, say, in this lecture and as others. All right, I hope you found this somewhat useful, and we'll see you again next time. Thanks, everybody. Take care.